Exercise 9.3, question number 18. Find the sum to n terms of the sequence 888, 888, 8888, and so on. Let us solve this question number 18. Here we can see that this is not a GP, because if we divide 88 by 8 we will get 11, and if we divide 888 by 88 we will be not getting 11. So this is not a geometric progression. So, but this can be reduced into geometric progression. Let us see how we can do that one. So, what we have to do here, find the sum to n terms of the sequence 8, 88, 888, and so on. So, let Sn equal to 8 plus 88 plus 888 plus 8888 and so on. Now, in all these kind of questions are very similar of this kind, that is, it may be like find the sum to n terms of the sequence 7, 757, 777, 7777, and so on. Maybe 333, 333, 3333, and so on. So in all these type of questions, what you have to do is, in all the numbers, which digit is being repeated here, that is 8. So we will take out 8 common from the series, and this is up to n terms. Here I have written Sn equal to this up to n terms. It's not infinite, up to n terms, because if it will be infinite, then obviously the sum will be also infinite in this case. So therefore Sn equal to, taking the common digit in all the numbers, that is 8 up to n terms. So we will get 1 plus 11 plus 111, that's 111 plus 1111, and plus so on up to n terms, Then next, therefore Sn equal to, next what you have to do is, you have to multiply this whole whatever we have got number by, you have to multiply it by 9 and divide by 9. Why we are multiplying with 9? We will see that. So multiplying and dividing by 9, 8 by 9 into multiplying whatever numbers are in the bracket with 9, this will become 9 plus 11 into 9 is 99, 111 multiplied by 9, that is 999, plus 1111 will multiply with 9, and it will become 9999, plus so on up to n terms. So up to n terms. Now next, Sn equal to 8 by 9. Now 9 will write in terms of 10. How we can write 9 in terms of 10? 9 can be written as 10 minus 1, plus same way 99 can be written as 100 minus 1, plus 999 can be written as 1000 minus 1, plus then 9999 can be written as 10,000 minus 1, and so on, that is up to n terms, So therefore we can say that Sn equal to, now in this one we'll write this 10, 100, 1000, so on in compact form. So this will be Sn equal to 8 by 9, and this will become 10 minus 1, plus 100 can be written as 10 square, and then we have minus 1, then 1000 can be written as 10 cube. So we will have 10 cube minus 1, and plus 10,000 can be written as 10 raised to 4, and there is minus 1 also with that, and plus so on up to n terms. So if you follow the same pattern, you can see that this is 10, this is 10 square, this is 10 cube, this is 10 raised to 4 minus 1. So the nth term will be 10 raised to n minus 1. So this will be our last term. This time there is no need to write n term, nth term. So now what we are, you can see here, if you just see only the number 10, 10 square, 10 cube, 10 raised to 4, so on, they are in GP. So we'll separate them, and this minus 1, they are all are that in another bracket will keep. So let us do that one. Therefore, Sn equal to 8 by 9. Now here we are having a single bracket. This will divide into two parts, one containing only 10, 10 square, 10 cube, and the other containing minus 1. So this will become 10 raised 10 plus 10 square plus 10 cube plus 10 raised to 4 plus so on till 10 raised to n. Now minus 1 is coming how many times? There are how many brackets of this kind? 10 minus 1, 10 square minus so on. You can see that there are n brackets, so that means minus 1 is repeating n times. So minus 1 into n, the total of minus 1 will be, because minus 1 is coming n times, so the sum of minus 1 will be minus n. So minus n. Now therefore Sn equal to 8 by 9. We'll just apply here, because this is GP, we'll apply here the sum to n terms of his GP. So what is the formula? A into r raised to n minus 1 over r minus 1. So what is A here? 10. What will be r? 10 square by 10, that is 10 again. So 10 into A into r raised to n, that is 10 raised to n minus 1 over r minus 1, that is 10 minus 1 minus n. So this will give us, therefore Sn equal to 8 by 9. It will become, if you want, we can just simplify it. Multiplying this 10 inside the bracket, this will become 10 raised to n plus 1 minus 10 over 9 minus n, and this will give us, therefore Sn equal to 8 by 81. This will become 10 raised to n plus 1 minus 10 minus 9n. So this will be the sum of n terms of the sequence which is given here. Question number 19. Find the sum of the products of the corresponding terms of the sequences 2, 4, 8, 16, 32 and 128, 32, 8, 2, 1 by 2. So solving 19th one. Now in this one, what we'll do is we have to multiply 2 and 128, then second term of first sequence and second term of the second sequence, third term of the first sequence and third term of the second sequence, and in the same way fourth and fifth also has to be multiplied with the fourth and fifth of the second sequence. So and what it says, find the sum of the product, and then we have to find its sum. So let us do this one. So the product of the corresponding terms of the two sequences, the product of the corresponding terms of both sequences of the two sequences of the two given sequences, that is equal to 2 will multiply with, here first let me erase this one, so equal to 2 into 128, then we will multiply 4 with 32, 4 into 32, then 8 will multiply with the third term here, that is 8, 8 into 8, then 16 will multiply with the fourth term, that is 2, so 16 into 2, then this 32 will multiply with the fifth term of the second sequence, that is half, so that is equal to 2 into 128, so this will become 2, 28 double is 56, So 256. Then 4 into 2 is 8, 4 into 3 is 12, 128. Then 8 into 8 is 64. 16 into 2, that is 32. And 32 into 1 by 2, that is 16. Now find the sum. So we have to find the sum of these terms, and we can add them simply, but that is not the way to be done, because we have to use we have to solve it by using formulas. That will be the right way of doing it. And you can easily see here, if we divide one if we perform the operation here, a2 by a1, 128 by 256 will be getting 1 by 2, 64 by 128 again 1 by 2, 32 by 64, that is 1 by 2, and 16 by 32, that is 1 by 2. So this is a GP, and we'll apply the formula of n terms of a GP. Here, let A1 equal to 256, A2 equal to 128, A3 equal to 64, A4 equal to 32, A5 equal to 16. Now, what we are having is A2 by A1, that is equal to 128 by 256, that is half. See, in mathematics, we cannot say that seeing from the sequence we can tell that it is GP. We have to prove that it is GP. So A2 by A1 is 1 by 2, then A3 by A2, that is equal to 64 by 128. So that is also 1 by 2. Then A4 by A3, and that is 32 by 64, and that is also 1 by 2. And same way, if you find A4 by A5 by A4, that is equal to 16 by 32, and that is also 1 by 2. Therefore, what we are getting, A2 by A1 equal to A3 by A2 equal to A4 by A3 equal to A5 by A4. So that is equal to 1 by 2. Therefore, uh, the new sequence obtained, therefore the new sequence here, the new sequence obtained is a GP, is a GP, and with so there is no need to write this, and with A1 equal to 256 and R equal to 1 by 2. So now how many terms are there? 1, 2, 3, 4, 5. So we'll find S5. So that we'll do the next page. So therefore S5 equal to, what is the formula? That is A into R raised to n minus 1 over R minus 1. So A into R raised to 5 minus 1 over R minus 1. And before that, let me draw a line here. So now let us put the value of therefore S5 equal to, what is our A1 or A, that is equal to 256. So 256. What is R? R is 1 by 2. So 1 by 2 raised to 5 minus 1 over 1 by 2 minus 1. So this will give us therefore S5 equal to 256, 1, 2 raised to 5 is 32 minus 1 over half minus 1, that is minus half. Now simplifying this further, we will be having S5 equal to 256. This will become 1 minus 32, that is minus 31 over 32, and this minus half can be taken in the numerator. will become minus 2. And we know that if you multiply 32 with 8, here 8 into 2 is 16, 1 carried over, 8 into 3 is 24, 24 plus 1 is 25. So these two will be cancelled out and we'll get here 8. So now uh, just so therefore S5 will be equal to minus 31 into minus 2, that is plus 64. So 64 into 8. Therefore S5 equal to 8 into 4 32, 3 carried over, and 8 into 6 is 48, 48 plus 3, that is 51. So sum of the 5 terms of the new sequence will be 512. So before we here, just again I am repeating that once we have got this new sequence, do not add them simply, because what we have to do is here we have to work it out according to the syllabus in class 11th, and that is we'll be adding these terms with the help of either AP or GP, but they are not AP, so they are forming a GP. So we'll use the formula of sum of n times of a GP. So this is how we will be solving this one, and with this question is complete. Question number 20. So that the products of the corresponding terms of the sequences AR square, so on till AR is to n minus 1, and capital AR square, so on till capital AR is to n minus 1 form a GP, and find the common ratio. So let us solve this 20th one. So solution number 20. We'll find the new sequence now. The new sequence is, so we'll multiply first term of the first sequence and the first term of the second sequence. So that will be a into small a into capital A. Then we will have AR into capital AR, and AR square into capital AR square, and so on. AR raised to n minus 1 multiplied with capital AR raised capital R raised to n minus 1. So now let us see whether this forms a GP or not. For GP we know that the ratio of the second term and first term should be equal to the ratio of third term and second term, and so on. Here let's suppose this is A1, this is A2, this is A3. So here A2 by A1 equal to AR capital AR over small a capital A. So both A and A cancel, capital A and capital A is cancelled. So we'll be getting R capital R. The next, let us find the ratio of A3 and A2. That is equal to A R square into capital A into capital R square divided by A R into capital A into capital R. So A and A cancel out, capital A and capital A also cancel out, and small r square will be divided by small r, and capital R square will be divided by capital R. So we will be getting small r capital R. So this is our 1, this is our 2. Therefore from 1 and 2, from 1 and 2, what we can say that the sequence is a GP. From 1 and 2, the new sequence is a GP, and what is the common ratio? And common ratio equal to here, because we have used R, we cannot use the small r, neither we can use this capital R. So let us take R dash equal to small r into capital R. So this is our common ratio, that is small r capital R. So with this, question number 20 is complete. Question number 21. Find 4 numbers forming a geometric progression in which the third number is greater than the first term by 9 and the second term is greater than the fourth by 18. So let us solve this one. Solution number 21. let the four numbers be A1, A2, A3, A4. Let A1, A2, A3, A4 be the four numbers with common ratio as R. Let A1, A2, A3, A4 be the four numbers with common ratio with common ratio equal to R. For let A1, A2, A3, A4 be the four numbers with common ratio equal to R for the required GP. For the required GP. For the required GP, and therefore we have what is given to us, that is find four numbers forming a geometric progression in which the third term is greater than the first term by 9. That is A3 minus A1 will be equal to 9. How we got from here? In which the third term is greater than the first by 9. That means the third term is bigger, and from that if you subtract the first term, what we will be getting is 9. So A3 minus A1 equal to 9. So that is equation number 1. Uh, but and what is more given to us, and the second term is greater than the fourth by 18. Also if we apply the second condition, that is here second term is greater than the fourth one by 18. So that means A4 minus A2 equal to 18, and let this be equation number 2. So therefore we have, what this will imply is we will apply the formula of AN, that is the nth term of a GP. So what is AN? A1 into R is to n minus 1. So A3 can be written as A1 R square minus A1 equal to 9, and from 1. And second one we can write as A1 one number less than 4, that is R cube, minus A2 can be written as A1 R, that is equal to 18 from second one. Therefore now let us dividing 2 with 1. Dividing 2 with 1, what we will be having, that is this can be still considered as 2, 1 only, and this can be considered as 2 because we have not done any substantial change in this one. So what we are doing is dividing second with first. So that means A1 R cube minus A1 R divided by A1 R square minus A1, and that is equal to 18 over 9. So from here in the numerator and denominator we can take out A1 common, and also from the numerator we can take out R common. So A1 R remaining will be R square minus 1 over A1 can be taken out common, the denominator will be getting R square minus 1 equal to 2. So R square minus 1, R square minus 1 cancel out, A1 and A1 cancel out. Therefore we can say that R equal to 2, and let this be 3. So now we'll put this third one in equation number 1, that is here we can put in this one. So therefore putting 3 in 1, we have, what we will have, putting 3 in 1, this is our R equal to 2, we'll put in 1, so we'll be getting A1, what is R2, so 2 square minus A1 equal to 9. So what is 2 square? 4. So 4A1 minus A1, that is 3A1 equal to, implies 3A1 equal to 9. Therefore What is a1? A1 equal to 3. Now what we have is got is here a1 equal to 3, and what we have to do in this particular question is find the 4 numbers forming a geometric progression. So we will be finding a1, a2, a3 and a4. So we are having a1, we are having r, so it is simple now. Therefore required gp is, therefore required gp is a1, a1r, a1r square and a1 r cube. That is, what is a1? 3. What is r2? So 3 into 2, 3 into 2 square and 3 into 2 cube equal to 3, 6, 4 into 3, that is 12, and 8 into 3, 24. So this is the required GP in our question number 21. Question number 22. If the PH, QH and R terms of GP are A, B and C respectively, prove that A raised to Q minus R, B raised to R minus P, C raised to P minus Q is equal to 1. So let us solve question number 22. Now since here R has been used, so we will be not taking the common ratio as small r, and neither will take the first term as A. So let us take capital A as the first term and capital R as the common ratio. Let capital A equal to first term of the GP, first term of the GP, and let capital R equal to common ratio of the GP, common ratio of GP. So therefore, what is given to us pth term, that is AP. AP means capital AP will write AP is equal to, that is small a. So if we apply the formula of AN, we will be getting AN, this can be written as A into R raised to, again R we have taken as capital R. So A into capital R raised to P minus 1 equal to A. So let this be question number 1. Then we have QH term as B, that is AQ equal to B. Therefore we can write A R raised to Q minus 1 equal to B, and this will be equation number 2. Similarly, what is given to us, the rth term is C, that is AR equal to C. Therefore AR, again for applying the formula of AN, so this will become A1, or because we have taken here our A1 is capital A, so A into R raised to n minus 1, that is our, what is our n? N is here R, so A capital R raised to R minus 1 equal to C. So this is our equation number 3. Now what we have to prove is that A raised to Q minus R, B raised to R minus P and C raised to P minus Q is equal to 1. So let us solve the left hand side. So therefore A raised to Q minus R into B raised to R minus P into C raised to P minus Q, that is equal to, what is our A, small a, we'll put the value of that, that is capital A into capital R raised to P minus 1, and over that we'll put the power of Q minus R into B. What is small b? A capital R raised to Q minus 1, and what is the power? R minus P multiplied by C raised to P minus Q. What is our small c? Capital A R raised to small r minus 1, and the whole power is P minus Q. So equal to, and we know that whenever base is same, we have to add the exponents. So here A is having the same base, here also A is having same base, here also A is having the same base. So we can write this as A. What is the exponent? Q minus R. So Q minus R plus, why we are adding? Because base is same, plus here the exponent of a is r minus p and not q minus 1, because that is the exponent of capital R in this inside the bracket. So plus this will become r minus p plus p minus q multiplied by, now same thing for r. So R is here, here also R, we are having capital R, here is capital R. So now we can add the exponent of these capital R. So this will become R raised to P minus 1 into Q minus R plus Q minus 1 into R minus P plus R minus 1 into P minus Q. So equal to, if you see here, minus R plus R cancel out, minus P plus P also cancel out, and Q and minus Q cancel out. So we are getting A raised to 0 into, same way here, into R now. Let us solve this. So we will be getting here R raised to PQ minus PR minus Q, and this will be plus R plus QR minus QP minus R plus P plus RP minus RQ minus P plus Q. So now we'll cancel those terms which can cancel out. PQ is here. Let us check if anywhere minus PQ is there or not. PQ is here. Yes, this is minus QP. PQ and minus PQ or minus QP both are same thing. Minus QP and PQ are same thing, so they will be cancelled out. Similarly, we are having minus PR, that can be cancelled with the help of RP. Then minus Q and plus Q cancel out. Plus P. So continuing with our work, this is minus P and plus P cancel out. Then next we are having plus R minus R cancel out. QR minus RQ cancel out. So all the terms have been cancelled out. Therefore, we can write this as A raised to 0 into R raised to 0. And we know that, of course, we already know that here the term, that is capital A and capital R, cannot be 0. That is not possible because ratio cannot be 0, because in that we have to find A2 by A1. So we assume that capital A and capital R both are non-zero, therefore we will be getting this as 1 into 1, and that is equal to 1. So therefore what we get our required result. And what is that? Therefore we can say that we will be writing the same thing, that is A raised to Q minus R, A raised to Q minus R into A raised to Q minus R into B raised to R minus P. So into B raised to R minus P into C raised to P minus Q into C raised to P minus Q, and that what we have got as 1. Let us see here. Here also we may have written the same thing here in the beginning. You can see it here. I'll just mark it. This is A raised to Q minus R into B raised to R minus P into C raised to P minus Q. So that is what we have written here. A raised to Q minus R into B raised to R minus P to C raised to P minus Q, and this is equal to 1. So this is our required solution. So let us write this again. So this will become here. So this is what we are getting. A raised to Q minus R into B raised to R minus P into C raised to P minus Q equal to 1. So with this, this question number 22 is complete. Question number 23, if the first and the nth term of a GP are A and B respectively, and if P is the product of n terms, prove that P square equal to AB whole raised to n. So solving question number 23, the first and the nth term of the GP are A and B. So let A1 be the first term. Let A1 be the first term, and let A1 be the first term of the GP. A1 is the first term of the GP, and R equal to common ratio. R equal to common ratio. Therefore, what we are having, what is given to us, A is the first term. So that means A1 is equal to A. And what is the nth term? That is B. And An equal to B. And what it says, and if P is the product of n terms, prove that P square equal to AB raised to n. Also P equal to A1 into A2 into A3 into so on till the nth term. So now what we'll do is we'll write each term here, A2, A3, so on, by using the formula of the nth term, that is An equal to A1 into R raised to n minus 1. So therefore we can say that P equal to A1 is A, A2 can be written as AR, A3 can be written as AR square into so on, and this An is nothing but that is A into R raised to n minus 1. And now therefore P equal to this can be written as, here if you see that A is coming how many times, n times, this will become A, this is 1 plus 1 plus so on, there is n times, so A raised to n into R. R is 1 plus 2 plus 3, because we know that whenever base is same the powers are added, 1 plus 2 plus so on till plus n minus 1. And therefore we'll be getting P equal to A raised to n into, and what is this 1 plus 2 plus 3 plus so on, if you see it very carefully, this is an AP, its common difference is 1, so we'll use the formula of n terms of a AP, sum of n terms of a AP. So that is R, what is the formula of Sn for an AP, that is Sn equal to n by 2 A1 plus An. So n by 2, what is n here? Number of terms are, how many number of terms are there? They are not n but n minus 1, so n minus 1 by 2. And A1 plus An, so what is A1? That is 1. What is the nth term in this case? It is n minus 1. And therefore we can say that P equal to A raised to n into R raised to n minus 1 over 2, and simplifying this will be getting into n. So what we are getting is, here is P equal to A raised to n into R raised to n square minus n over 2, and let this be question number 1. And further what is given to us, and P is the product of n terms, prove that P square. So P square is equal to A raised to n into R raised to n square minus n over 2, and we'll do the square of this, so we'll be getting P square equal to A raised to 2n into R raised to n square minus n over 2, and this into 2, so 2 and 2 cancel out, so we'll be getting therefore P square equal to A raised to 2n into this will become R raised to n square minus n only. And now what we can do is, from both we can take out n common, so this will become therefore P square equal to A, this will become 2A square into R raised to, this will become n minus 1, and outside we can take this as n. Now if we what we have to do is, because what is given to us, is also given to us that an equal to b. Here we are having an equal to b. So we'll take the help of this. Also an equal to b. Let this be suppose till now we have done till question number 1. So let this be question number say 2, and an equal to b, and we'll be applying here the formula of nth term of a GP. So an equal to b, and that can be written as a1 r raised to n minus 1 equal to b. So what we'll be doing here, but what is our a1 implies a into r raised to n minus 1 equal to b. Now let this be question number 3. So what we can do is we can put the value of a into r raised to n minus 1 equal to b in equation number 2, that is putting 3 into. So but before that what we can do is we can break this a square as a into a. From 2 we have p square equal to, this can be written as a into a, just writing a square as in expanded form a into a, then we are having into r raised to n minus 1, and the whole power is there outside is n, implies p square equal to a into, now a into r raised to n minus 1 is our a into r raised to n minus 1. If you see that, then from equation number 3 this can be replaced with b. So we can write here in place of this what we can write is b. So a into b whole raised to n, from where? From 3. Therefore what we are getting is p square equal to ab whole raised to n. So this is the solution of our question number 23. So this is how you will be doing it. Question number 24. So that the ratio of the sum of the first n terms of GP to the sum of n terms from n plus 1th to 2nth term is 1 by r raised to n. So solution number 24. Let a1 be the first term. Let a1 be the first term of the GP. First term of the GP. And here what is here, because we have to put that is the ratio is 1 by r raised to n, that is the sum of the first n terms divided by the sum of the terms from n plus 1th to 2nth term is 1 by r raised to n. Obviously the common ratio of the GP will be r, and r equals to common ratio. So now what we'll do is we'll find the ratio of the sum of the first n terms of the GP to the sum of terms from n plus 1th to 2nth term. Therefore we can say that Sn over, when we have to write the sum of terms from n plus 1th to 2nth term, what we can write is S2n minus Sn. Directly we can write equal to, now what is Sn? We know that sum of n terms of the GP is a into, just we'll apply the formula of sum of n terms of the GP. So that is a into, and how many terms are there to show that the sum of the first n terms of the GP to the Sn. So number of terms in this case are n. So a into r raised to n minus 1 over r minus 1, and this whole divided by S2n. What is S2n? Sum of the first 2n terms. So Sn will be S2n, in this case will be a into r raised to 2n minus 1 over r minus 1 and minus Sn. From here we can write the value of Sn, that is a into r raised to n minus 1 over r minus 1. Now this can be further simplified. Therefore Sn over S2n minus Sn equal to a into r raised to n minus 1 over r minus 1 whole divided by Now, from the in the denominator, we can see that a by r minus 1 is common, so that we can write as a by r minus 1. And here what we are having is remaining will be r raised to 2n minus 1. And if we open the take the minus in account, so we will be getting minus r raised to n plus 1. So now we'll simplify this also further. So here we can cancel this a over r minus 1, and here also a by r minus 1. So this will give us, therefore implies Sn over S2n minus Sn equal to r raised to n minus 1 over this minus 1 plus 1 cancel out. So we'll be getting here r raised to 2n minus r raised to n, and from both we can take out r raised to n common. So this will give us equal to r raised to n minus 1 over r raised to n. So what will remain here is r raised to n minus 1. Therefore, we can say that Sn over S2n is 2 here, S2n minus Sn equal to, so what we can do is we can cancel this r raised to n minus 1, and this also r raised to n minus 1, both are in the numerator and denominator, so they will cancel out, and remaining will be 1 by r raised to n. So this is our solution. And again, those who are may not be able to understand this, S2n minus Sn is nothing but this only, that is uh, sum of terms from n plus 1th to 2nth term. So we can write in that way, because S2n means sum of the first 2n terms and Sn means the sum of first n terms. So from the first 2n terms, we remove the first n terms, what we will be getting is the sum of the terms from n plus 1th to 2nth term. So this is our solution of question number 24, and with this it is complete.